I am going to try to finish up Chapter 17 today on electric potential, and the topic we'll be dealing with mostly is how to use this concept of change in potential, potential difference, to tell us about the behavior of electric fields inside matter, particularly inside insulators. We already have some idea of what happens inside a conductor, and we'll start there first as an example. And we had a question at the very end of class last time, so I want to start with this example of a capacitor. So we have two metal plates. One is positively charged, and one is negatively charged. Okay, so capacitor inside the gap in between the two plates, and let's say this distance is S, and what is S equal to? Let's say S is 2 millimeters, so 2 times 10 to the minus 3 meters. It's a charge plus Q and a charge minus Q, and let's say point A, location A is right on the edge of the positive plate, and location B is exactly opposite to it on the negative plate. And what do we know about the field inside a capacitor? Inside this capacitor gap, the electric field is pointing what direction? To the right, okay. And the magnitude of it is what? Q over A over epsilon 0. You had to use this last night for a homework set. So the issue is that it's in the approximation that this distance S is much smaller than the size of the plate. So the radius of the plate is stretching far beyond what we can see right on the board. It's a small gap, and so the field is mostly uniform inside. We can use this constant field approximation. So in fact, I'm not even going to worry too much about the charge or calculating the field from the area. Instead, let's just say that we know the potential difference, VB minus VA. And let's say that's negative 1,000 volts. And let's double check that the sign is correct, because if we're going, VB minus VA is telling us we're going along a path that goes from A to B, and we're going in the direction of the electric field, so the potential difference should be negative. Okay. So what's the electric field? Well, VB minus VA is negative E dot delta L. And I already know the direction, so let me just find the magnitude. The magnitude is going to be the magnitude of VB minus VA over the magnitude of that distance. And it's really delta x here, right? Because we're just looking at EX delta x. It's only in the x component. So that delta x is the same as the distance S. Okay, that's the separation. So we have 1,000 volts divided by 2 times 10 to the minus 3 meters. And that gives you an electric field of 5 times 10 to the 5th volts per meter. Okay. Now, I've got the same capacitor, same charge on the plates, same distance between the plates, same everything, except I'm going to do one thing. I'm going to insert in between the plates a slab of metal. So I'm just going to put a great big parallel sheet of metal that has some thickness. This is metal here. Okay, and so this plate is still positive. This plate is still negative. And let's say the distance, let's say this is 0.5 millimeters from A to this surface of the metal. This is a 1 millimeter thick metal slab, and this is another 0.5 millimeter. Okay. What happens? What happens to the metal? Okay, let's be careful. It's neutral. It's a neutral slab of metal. So is it going to still have? Is it going to end up with a net charge? No. But what is going to happen? It's going to polarize. It's going to polarize. So what's going to happen on this surface? Becomes a negatively charged. Okay. So and this side positive. Okay. So I just want to be careful about the language. It's polarized, then it's still neutral. The net charge on the entire metal slab is 0, but it has a separation of charge now, negative on one side, positive on the other. Okay. So here's something, an idea that we should all be familiar with by now because it showed up on homeworks and quizzes and again on the tests, right? What is the net electric field inside the metal? 0. Okay, so E net's equal to 0. But that net electric field is due to two contributions, right? We still have the electric field of our original capacitor, which is pointing in what direction? To the right. So I'll say this is E of the capacitor. So that means what? E of the induced charges or the polarization charges on the surface of the metal has got to point to the left. And what do we know about that E on the metal? That electric field is got to be the same as the E on the capacitor. So the electric field of the metal is going to be what we just worked out. The magnitude of it is going to be 5 times 10 to the 5th volts per meter. Okay. Now, our job is to figure out two things. One is, well, it's kind of one related thing, but how much charge is on each side of the metal, and then what is the new electric field inside the capacitor, or inside the gap, inside these air gaps within the capacitor, a point here and a point here. And let's think about the metal first. Squint your eyes and kind of hold your nose and ignore the presence of the plates for just a second. And just think about this polarized slab of metal. Here's one surface that's positively charged. Here's one surface that has the exact opposite negative charge, parallel to each other. Inside, what does that look like to you? It looks like another capacitor, doesn't it? It looks kind of like another capacitor. So the electric field due to the metal, the charges on the metal, should in fact be equal to Q over A over epsilon naught. Well, it's the same area as our original capacitor. There's no dependence on the distance, right? Because if the gap is small enough, then the field is uniform. So how much charge ends up on this side? Let's put it this way. Let's say this is some positive Q, all right, and this is negative Q. How much charge ends up on this surface? Negative Q, right? Because if this field is the same, then this charge in this formula has got to be the same. And so you end up polarizing. Negative Q on this side, positive Q on that side. Now, squint your eyes and hold your nose again and look at just sort of this half of what we've got. We've got positive Q here, negative Q here on this surface. In between, what have we got? Another capacitor, right? Now it's sort of like having two capacitors, one after another. So what do you think the electric field in here is going to be? Should be the same as it was before. Should be the same as it was before. Approximately, okay, because we're ignoring one thing. We're ignoring the fringe field, okay? This polarized slab, okay, behaves like a capacitor itself, but there is a small amount of field that it makes outside of its borders, okay? We talked about that being the fringe field, the field outside of a capacitor. But if we ignore that small amount, it's going to be small compared to the field inside. The electric field in here should be 5 times 10 to the 5th volts per meter. The electric field in this air gap should be 5 times 10 to the 5th volts per meter. And in here, the net electric field, we said, is equal to 0. Okay? So now we have sort of 3 regions, one after the other, with 3 different uniform electric fields. Okay, and there's a lot of stuff here, so let me kind of clean this up. And let's see, we'll get rid of this. And we still have our 2 locations, A, which is over here, and B, which is over here. Okay? So here's the question. Here's the question. Without the metal slab, when we found potential difference A to B, it was negative 1,000 volts. Then we put this metal slab in between. What's VB minus VA now? Okay, we have 2 popular answers. Some people are saying answer number 5, which is exactly the same as it was before. Some people are saying, well, it's half of what it was before. Well, how did we deal with a situation like this last time? You have a path that goes from A all the way over to B, right? As you traverse the imaginary path, you cross through 3 different regions of uniform field, differing uniform field, right? From A to this surface, it's 500 volts per meter, but then across this 1 millimeter distance, it's 0, and then it's back to 5 times 10 to the 5th volts per meter again, okay? So how do I deal with a situation like that? How do I find the total delta V? What do? We add them up, right? We take one at a time, find the delta V across the first region, then across the second region, then across the third region, add them up. So we have an E1 dot delta L1, right? Minus an E2 dot delta L2 minus an E3. Don't need this anymore, so erase this. E3 dot delta L3. And so we have E1, the X component of E1 is 5 times 10 to the 5th volts per meter. And the distance across that first region is half a millimeter, right? 0.5 times 10 to the minus 3 meters. Minus, what's E2? E2 is 0. E2 is 0. And then minus 5 times 10 to the 5th volts per meter times another half millimeter distance. So that's the same, so we can add them up. Just say it's going to be twice that. What do you get? Should be negative 500. Okay, so it does actually reduce the potential difference. The field, placing the metal slab inside the capacitor doesn't change the field in the air gap, doesn't change this field in the air gap, but does reduce the field inside to 0, okay, because it's a metal at static equilibrium. So it's sort of polarized perfectly so that we cancel out the net electric field inside, and then when you take the potential difference, you're going through a rather large region where the electric field is 0, giving you a delta V equal to 0. You've reduced the potential difference overall. Okay? Questions? All right. Now let's try thinking about a different situation. We're going to instead of inserting a metal slab, same capacitor, same charge on the capacitor plates, but now it's a plastic slab. So it's an insulator. It has the same dimensions. It's 1 millimeter thick. It's right in the middle between these two capacitors. And ultimately, we want to eventually figure out what the potential difference is from A to B again. Before we talk about it too much, let me skip this for just a second. Originally, we had a delta V without the slab in there of negative 1,000 volts, and then we insert the plastic slab. Just use your intuition. Take a guess. Talk it over. See what you think. What's the new potential difference going to be? We saw for when we put the metal slab in there, it went down to negative 500 volts. Is it going to be the same? Is it going to be different? How much different? Okay, so everybody's sort of gut feeling is a good one. We would think that if the metal slab made the potential difference go down to negative 500 volts, we would expect the plastic slab to give us a potential difference of somewhere between negative 500 and negative 1,000, right? It's going to reduce it, but not as much. Why not? Why does this seem to make sense? Okay, the electric field inside, for one thing, isn't necessarily going to be zero, right? Because a plastic slab doesn't have mobile electrons, right? So how would I draw this? What's going on inside here? What do I need to draw? Yeah, polarized atoms, right? Induced dipoles, something like that. And like you guys said, there's no mobile electron seed, so there's no guarantee that E net is going to be equal to 0. But something happens to E net in here. And at any particular point, well, it might be hard to say what E net is doing because you've got all these polarized molecules in here, and depending on where exactly your observation location is, you could have, the net electric field pointing one way at one location or a completely different way at another location, depending on where you are. So it's a little bit messy, and it's hard to figure out. But we can use potential difference to reason it out in terms of what happens to the average electric field. If we were to kind of smear it all over and just look at an average, what's going on with the average electric field inside? And here's how it works. Let's just look at this polarized slab. If I were to kind of just isolate the polarized slab and think of, okay, we got all these induced dipoles. The applied field is making positively charged dipoles on the right, negatively charged dipoles on the left. So if I were looking at the electric field, and I just want to say the electric field due to these dipoles alone, at a location here, those dipoles would make an electric field pointing in what direction? To the right. Okay. So this is E due to the dipoles, right? And over here, the electric field due to the dipoles will be pointing that way, to the left? To the right, yeah, because the negative sides are closer over here, right? So just think about what would happen with one dipole, right? If you had one dipole, you've seen this. E points that way. E points that way, and then how does E point down here? To the left. So I can just sort of do that en masse, and I can see that this is going to be the pattern of electric field just due to those dipoles. We still have the electric field due to the capacitor, but I'm just looking at the field due to the dipoles. I'm going to choose a path to calculate a potential difference. It's going to start over on the right. It's going to go underneath underneath the plastic slab, underneath all the dipoles, over to the left, and then straight through back to where I started from. Okay. If I go round trip, if I go delta V round trip, and my path ends up where it starts, what should I get for delta V? Should get 0. Okay, and this is important property to know. Okay, it comes from the idea of path independence, where we said the path doesn't matter going from A to B. So if you go from A to B along any path, you get some potential difference. Go back from B to A, you get the same magnitude but opposite sign of potential difference. Round trip potential difference is going to give you 0. Okay? Well, let's look at the signs of the potential difference along some parts of these paths. And let me do this with a little program here. Let me get some dipoles. So in this program, you can just kind of drag a positive charge here and a negative charge here, and then click and show the electric fields due to these charges, etc. And let me do an example I already have written up. Let's get sources and get the dipoles. So there's a bunch of dipoles. Okay, the negatives are blue and the positives are red. Okay, so let's calculate the electric field at some places. There. Hey, what's going on? There we go. That's better. Okay, so it's doing the typical dipole pattern, right? Pointing away, pointing towards, curling around. Let me think about the potential difference. If I start here and go to here in the direction of the electric field, the potential difference along that part should be what? Positive or negative? Should be negative. Okay, so all right, I have to do it all in one sweep, so let's talk about it as we go along. I start here, I go around this semicircle over to here. Okay, so here's my starting point, that's my ending point. What sign of potential difference would you get? You start off with a path that's pointing downward, right? And it's kind of perpendicular to that electric field, so that should give you about 0. But notice as you're moving along this path, how does the electric field point? It's always going to have a component that is more or less in the direction of your path, right? Can everybody see that? Like, you can especially see it right here. I mean, I'm going basically in that direction. And here as well, I'm kind of going up. Then it starts to get more and more perpendicular, so it doesn't quite contribute as much. But overall, if I add the whole thing up, I should get negative, right? And then I go from here to here. That should give me what? Negative, because I'm going again in the direction of the electric field. If the round trip potential difference gives me 0, what should I get when I go through the interior? Should get a positive. Let's try it out. So I start here. Okay, it's giving me negative, I don't know if you can read it, negative 12.0 volts. And the blue indicates a negative potential difference. Red indicates a positive. Looks pretty blue. And my path is kind of shaky, but that's okay. Looks pretty blue. And it's all blue so far. And then it starts to get messy. Then it kind of goes a little bit blue, but then it gets really red again. And things are just going crazy. And then we go back. Okay, so it doesn't quite go to 0. It says negative 0.2. But that's due to round-off error in the calculation. But you can see the colors in here, right? I mean, there's a lot of red fuzziness indicating a pretty large positive potential difference inside, okay? You saw how the field was kind of going nuts in terms of the direction. But overall, you're getting a positive potential difference just due to the field of the dipoles, just due to the field of the dipoles inside. So that says, what's that tell us? If we're going in the direction of the field of those dipoles, so here's the dipoles. If I went in that direction, if that was my delta L, and I got a positive overall, then the average electric field just due to the dipoles has got to be pointing in what direction? It's got to be pointing to the left. Okay, so that's the electric field due to the dipoles. All right, so that's the basic argument. We use this potential difference to determine how this field must point, but it's still inside the capacitor. So here's our capacitor again. This was negative, and this was positive. We still have an electric field due to the capacitor pointing in that direction. But is E of the dipoles equal to E of the capacitor? You think that's going to be true? Probably not, right? In a metal, it was. In a metal, you have sort of the perfect amount of polarization to cause this electric field to cancel out. the dipole electric field isn't large enough to cancel the field of the capacitor out, but it does reduce it. Note, and so the net electric field we get is something smaller, but still pointing in the same direction. So if I draw the plastic now, I have E net inside, which is smaller. I have E in the air gaps, which should be approximately what? The field in the air gaps change much? Did it change much for the case of the metal? No, so it's probably not going to change much for the case of the plastic, right? Because there's even less polarization going on. So we have the original E of the capacitor here. We have the original E of the capacitor here. And we have a reduced E net inside, or average E net inside. There's actually a relationship, experimental relationship, or empirical relationship, that tells us how much that E net is. And that E net inside is equal to the electric field, and I'll call it the applied electric field, which is the field due to the capacitor in this case, divided by a constant K. This capital K is called the dielectric constant. And it's a property of a material. Okay, so it's a material property. And for most ordinary materials, sort of well-behaved materials, there are lots of exceptions to this, but K is typically greater than or equal to 1. Okay? So if I have a number greater than 1, I'm dividing by a number greater than 1, my electric field has gone down. It's less than the original applied field. Okay? Examples of this value. I think I have some examples here. K for air. Well, K for a vacuum, by definition, has got to be just 1 because the field isn't affected by anything. K for air just slightly affects this applied electric field. It's 1.00054, something like that. For a typical plastic, it's somewhere between 2 and 3, okay, approximately. Paper, it's something like 3.5. Glass, it's approximately 5. So these are just giving you the values of how much the field is affected. Okay, a bigger dielectric constant means more polarization inside, meaning a greater reduction in that overall electric field. Okay, so this is kind of a long chain of reasoning. We used a lot of stuff here, but we've worked out that the potential difference should be reduced, not as much, but if we knew not as much as a conductor, but if we know that dielectric constant, we should be able to calculate it. So let's see if we could do that. Let's say, same situation. Let's say the dielectric constant of the plastic is 2. What's going to be the new potential difference from A to B? Think about what the value of the electric field is in each of those different regions, okay, just like we did with the conductor. Okay, so we have most of us saying negative 750 volts. Those of you said negative 250, you've got to be careful. We're talking about, again, the potential difference from A to B. So again, we're going through 3 different regions, right? One where we have the original electric field of the capacitor. So let's write it out again. We have E1x delta x 1 minus E2x delta x2 minus E3x delta x3. So E1 is still 5 times 10 to the 5th. First distance is still 0.5 times 10 to the minus 3. E2, the new electric field inside the plastic is what? 2.5 times 10 to the fifth, right? It's going to be the applied electric field due to the capacitor divided by the dielectric constant, which is 2. Okay, 2.5 times 10 to the fifth times 1 millimeter times 1 times 10 to the minus 3. Continue it down here. Minus 5 times 10 to the fifth times 0.5 times 10 to the minus 3. Okay, so add that all together. We have 2 times this, so it's like 5 times 10 to the 5 times 10 to the fifth times 1 millimeter, essentially, when you add this term and this term together. So that gives you negative 500 volts minus another 250 volts. So that gives you negative 750 volts. So our intuition works out from before, right? We expected the potential differences to be somewhere in between 1,000 or negative 1,000 and negative 500, and it works out. Okay. So yes, question. I said that this electric field is the net electric field inside the plastic, right? The dielectric relationship says that the net electric field inside your plastic is going to be the applied electric field, meaning the field that causes the polarization in the first place. In this case, that's the field due to the capacitor. Okay? So in this case, it's 5 times 10 to the fifth, the same electric field that we had before, okay, divided by the dielectric constant, which is 2. So the overall net electric field turns out to be 2.5 times 10 to the fifth. Okay? Okay? Other questions here? All right, so you have a question on a dielectric for homework. The point of all this is, and we'll come back to capacitors later in the semester, but dielectrics actually have very important technological purposes. Pretty much every capacitor that's used in a real-life situation has a dielectric in between the plates, okay, or in between the conducting plates. And this is kind of a contrived example. Typically, the dielectric fills up the entire gap. What's it for? Well, for one thing, you need to physically separate the two charged plates. You can't have them in contact with each other, or the charge will bleed off. Okay, and the other idea is that because of the polarization of the dielectric, the net electric field is reduced from what it would be if there was just a vacuum in there. The more you reduce that net electric field, the more you reduce that potential difference across the two plates, and then you can essentially, given the same potential difference, charge up the plates more. You can add more charge to the plates if you put a dielectric in between them. And that's useful because we want dielectrics to hold lots of charge on either side in order to get that energy back again if we want to then use it in a circuit or some other application. Okay, so we'll come back to this later in the semester, but it's important because it's actually used a lot in real life applications.